Ampacity is the maximum current a conductor can safely carry continuously without overheating or causing damage. Circuit protection is used to protect electrical circuits from overcurrent conditions such as short circuits or overloads. According to the National Electrical Code, NEC Table 310.16, a number 12 THHN conductor has an ampacity of 30 amps. To protect against potential overloads, it is recommended to limit the current on a conductor to 80% of its ampacity. For a number 12 THHN conductor, 80% of 30 amps equals 24 amps. According to the NEC, circuit breakers must be rated at or below the ampacity of the conductor they protect. In this case, because the maximum current the conductor is intended to carry is 24 amps, the appropriate circuit breaker rating is 20 amps. The question is why 20 amp breaker is required. Using a 30 amp breaker would allow the conductor to carry up to 30 amps, exceeding the recommended 80% load limit. This could lead to conductor overheating and potential fire hazards. Hence, the 20 amp breaker ensures the conductor is protected within its safe operating range. Limiting the current to 80% does not physically reduce the ampacity of the wire. It effectively limits the safe carrying capacity of the conductor to protect against potential overloads. To comply with NEC requirements and ensure proper circuit protection, it is necessary to use a 20 amp circuit breaker on a number 12 THHN conductor when limited to an 80% load. This ensures the conductor is not overloaded and maintains a safe operating temperature. When sizing conductors and overcurrent protection, several factors must be considered to ensure safety in compliance with the NEC. These factors include ampacity, temperature correction adjustment factors, conductor termination temperature ratings, and overcurrent protection device ratings. Ampacity is the maximum current a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The ampacity of conductors is determined by NEC Table 310.16, which provides ampacity values for various conductor types and sizes based on insulation temperature ratings and installation conditions. The table values are based on ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. When the ambient temperature exceeds 30 degrees Celsius, a correction factor must be applied to reduce the conductor's ampacity. These correction factors are found in the NEC Table 310.15b2. If multiple current-carrying conductors are bundled together or installed in close proximity without maintaining spacing, the heat generated by each conductor can raise the overall temperature and reduce the ampacity of each conductor. Adjustment factors are applied to direct the ampacity of the conductors. These adjustment factors are found in NEC Table 310.15 colon. Conductor termination temperature ratings are the maximum temperature that the conductor terminations, such as lugs or terminals in equipment, are designed to withstand. The NEC requires that conductors be sized such that the conductor ampacity after temperature correction and adjustment is not less than the termination temperature rating of the connected equipment. Standard termination temperature ratings are typically 60 degrees Celsius or 75 degrees Celsius. Overcurrent protection devices such as circuit breakers and fuses are designed to protect conductors from overloads and short circuits. The NEC specifies requirements for the selection and sizing of overcurrent protection devices to ensure that they will protect the conductors without causing nuisance tripping. The overcurrent protection device must be rated to protect the conductor's ampacity after temperature correction and adjustment factors have been applied. NEC Section 240.4d provides specific rules for the overcurrent protection of small conductors such as number 14, number 12, and number 10 copper conductors. These rules limit the maximum overcurrent protection device rating to specific values based on the conductor size. For example, a number 14 copper conductor is typically limited to a 15 amp overcurrent protection device. A number 12 copper conductor is typically limited to a 20 amp overcurrent protection device, and a number 10 copper conductor is typically limited to a 30 amp overcurrent protection device. These limitations are intended to protect the conductors from overheating and potential fire hazards. In summary, when sizing conductors and overcurrent protection, it is important to consider ampacity, temperature correction, adjustment factors, conductor termination temperature ratings, and overcurrent protection device ratings. Following the NEC requirements will help ensure that the electrical system is safe and reliable. Now let's delve deeper into the NEC requirements and provide some specific examples to illustrate these concepts. Let's consider a scenario where a number 12 THHN copper conductor is installed in a conduit with other current carrying conductors and an ambient temperature of 40 degrees Celsius. We need to determine the appropriate overcurrent protection device rating for this conductor. Step 1. Determine the ampacity of the number 12 THHN conductor from NEC table 310.16. According to the table, a number 12 THHN copper conductor has an ampacity of 30 amps at an ambient temperature of 30 degrees Celsius. Step 2. Apply temperature correction factors. Since the ambient temperature is 40 degrees Celsius, we need to apply a temperature correction factor from NEC table 310.15b2. For THHN insulation, the correction factor at 40 degrees Celsius is 0.87. Therefore, the corrected ampacity is 30 amps multiplied by 0.87, which equals 26.1 amps. Step 3. Apply adjustment factors for the number of current carrying conductors. If there are more than 3 current carrying conductors in the conduit, we need to apply adjustment factors from NEC table 310.15 current. Let's assume there are 6 current carrying conductors in the conduit, which requires an adjustment factor of 0.80. Therefore, the adjusted ampacity is 26.1 amps multiplied by 0.80, which equals 20.88 amps. Step 4. Determine the allowable overcurrent protection device rating. According to NEC section 240.4d, a number 12 copper conductor is typically limited to a 20 amp overcurrent protection device. In this case, the adjusted ampacity of the conductor is 20.88 amps, which is slightly above the 20 amp limit. However, NEC section 240.4b allows us to round up to the next standard overcurrent protection device rating if the conductor ampacity does not correspond to a standard size. Therefore, we can use a 25 amp overcurrent protection device in this case. Step 5. Verify termination temperature ratings. Ensure that the conductor terminations are rated for at least 75 degrees Celsius. If the terminations are only rated for 60 degrees Celsius, we must use the 60 degrees Celsius ampacity column in NEC table 310.16, which would require us to use a larger conductor size. In this example, we have demonstrated how to apply temperature correction and adjustment factors to determine the allowable overcurrent protection device rating for a number 12 THHN copper conductor. It is important to follow these steps carefully to ensure that the electrical system is safe and compliant with the NEC. Now let's consider another scenario where a number 10 AWG THHN copper conductor is installed in a raceway with 8 other current carrying conductors in an ambient temperature of 35 degrees Celsius. The conductors are supplying a continuous load. What is the maximum size breaker that can be used to protect this circuit? First, find the ampacity of a number 10 AWG THHN conductor from NEC table 310.16. The ampacity is 40 amps at 30 degrees Celsius. Second, apply the temperature correction factor. From NEC table 310.15b2, the correction factor for THHN at 35 degrees Celsius is 0.91. Corrected ampacity equals 40 amps multiplied by 0.91, which equals 36.4 amps. Third, apply the adjustment factor for the number of conductors. There are 9 current carrying conductors, so from NEC table 310.15 cone, the adjustment factor is 0.7. Adjusted ampacity equals 36.4 amps multiplied by 0.7, which equals 25.48 amps. Fourth, consider the continuous load. Because the load is continuous, the overcurrent device must be rated for 125% of the continuous load. This means the conductor must be rated for at least 125% of the continuous load before any dirting. Alternatively, the overcurrent device must be rated no higher than 80% of the conductor ampacity after dirting. Fifth, determine the maximum breaker size. The maximum breaker size is the lower of the values calculated in steps 3 and 4. In this case, it is 25.48 amps. According to NEC section 240.6a, standard breaker sizes are 15 amps, 20 amps, 25 amps, 30 amps, etc. Since 25.48 amps is not a standard size, you must choose the next lowest standard size, which is 25 amps. Sixth, verify the termination temperature rating. Ensure that the conductor terminations are rated for at least 75 degrees Celsius. If the terminations are only rated for 60 degrees Celsius, you must use the 60 degrees Celsius ampacity column in NEC table 310.16, which might require you to use a larger conductor size or a smaller breaker. In this example, the maximum breaker size that can be used to protect the circuit is 25 amps. It is important to note that this is just an example, and the specific requirements for each installation may vary depending on the specific conditions. Always consult the NEC and local codes for specific requirements. The 80% rule for circuit breakers and continuous loads is a critical safety measure within the NEC. It primarily addresses the potential for overheating and premature failure of electrical components when subjected to prolonged high current draw. Here is a more detailed explanation of this rule, its rationale, and its practical implications. The 80% rule, as it is commonly known, is formally addressed in NEC section 210.19a on for branch circuits and section 215.2a on for feeders. These sections stipulate that for continuous loads, the overcurrent device, such as a circuit breaker or fuse, must be rated no less than 125% of the continuous load. Conversely, this means the continuous load should not exceed 80% of the overcurrent device's rating. A continuous load is defined as a load where the maximum current is expected to continue for 3 hours or more. Examples of continuous loads include lighting in commercial buildings, HVAC systems, and certain types of machinery. The primary reason for the 80% rule is to prevent overheating of conductors, terminals, and overcurrent devices. When electrical components carry current, they generate heat due to the resistance within the materials. The amount of heat generated is proportional to the square of the current, as described by Joule's law, which states that power dissipated as heat P equals current squared I squared multiplied by resistance R, or P equals I squared R. Continuous high current levels can cause a significant temperature increase in these components. Conductors. The insulation of conductors is designed to withstand certain temperature limits. Exceeding these temperature limits can degrade the insulation, leading to a reduction in its dielectric strength and an increased risk of short circuits, ground faults, and ultimately, electrical fires. Terminals. The terminals where conductors connect to devices such as circuit breakers, receptacles, and equipment are also susceptible to overheating. High temperatures can cause the terminal connections to loosen over time, increasing resistance and further exacerbating the heat generation. Overcurrent devices, circuit breakers and fuses are designed to protect circuits from overcurrent conditions by interrupting the current flow when a predetermined threshold is reached. However, these devices are also subject to thermal limitations. Continuous loading at or near their rated capacity can cause them to overheat, potentially leading to nuisance tripping, reduced lifespan, or even failure. The 80% rule provides a safety margin to account for these thermal effects. By limiting the continuous load to 80% of the overcurrent device's rating, the heat generated is reduced, and the components operate at a lower temperature, extending their lifespan and reducing the risk of failure. Compliance with the 80% rule requires careful consideration during the design and installation phases of electrical systems. Load calculations. Accurate load calculations are essential to determine the expected continuous and non-continuous loads on a circuit. This involves summing up the power requirements of all connected devices and accounting for any demand factors or diversity factors that may apply. Overcurrent device selection. The overcurrent device must be selected based on the calculated loads, ensuring that it is rated no less than 125% of the continuous load. This may require selecting a larger breaker, or few them would be necessary for a non-continuous load of the same magnitude. Conductor size and conductors must be sized to handle the calculated loads, taking into account ampacity, directing factors for ambient temperature, the number of conductors in a raceway, and other relevant conditions. The conductor's ampacity must be sufficient to carry 125% of the continuous load plus 100% of the non-continuous load. Practical implications. The 80% rule has several practical implications for electrical installations. Increased breaker size. In some cases, compliance with the 80% rule may necessitate the use of a larger breaker than would otherwise be required. For example, if a circuit is expected to carry a continuous load of 16 amps, the breaker must be rated at least 125% of 16 amps, which is 20 amps. Rating of equipment. Some equipment, such as generators and transformers, may have nameplate ratings that do not account for continuous loading. In these cases, the equipment must be derated to 80% of its nameplate rating when supplying continuous loads. Design considerations. Electrical designers must carefully consider the potential for continuous loads when laying out circuits and selecting equipment. This may involve separating continuous loads from non-continuous loads, or using larger conductors and overcurrent devices to accommodate the increased capacity requirements. The 80% rule is a fundamental principle in electrical safety that helps to prevent overheating and failure of electrical components when subjected to continuous loads. By limiting the continuous load to 80% of the overcurrent device's rating, the rule provides a safety margin that reduces the risk of insulation breakdown, terminal connection failures, and overcurrent device malfunction. Compliance with the 80% rule requires careful load calculations, appropriate overcurrent device selection, and proper conductor sizing. By adhering to these requirements, electrical systems can be designed and installed to operate safely and reliably for their intended lifespan. Now let's talk about the specific code sections. NEC Section 210.19 A covers branch circuits. It states that branch circuit conductors shall have an ampacity not less than the maximum load to be served. Where a branch circuit supplies continuous loads or any combination of continuous and non-continuous loads, the minimum branch circuit conductor size, before the application of any adjustment or correction factors, shall have an allowable ampacity equal to or greater than the non-continuous load plus 125% of the continuous load. NEC Section 215.2 A covers feeders. It states that feeder conductors shall have an ampacity not less than the maximum load to be served. Where a feeder supplies continuous loads or any combination of continuous and non-continuous loads, the minimum feeder conductor size, before the application of any adjustment or correction factors, shall have an allowable ampacity equal to or greater than the non-continuous load plus 125% of the continuous load. In both cases, the 125% factor is applied to the continuous load to determine the minimum required ampacity of the conductors. This ensures that the conductors are capable of handling the continuous load without overheating. Now let's consider a practical example. Suppose you have a branch circuit that supplies a continuous load of 10 amps and a non-continuous load of 5 amps. To determine the minimum required ampacity of the branch circuit conductors, you would apply the following calculation. Non-continuous load plus 125% of the continuous load equals 5 amps plus 1.25 multiplied by 10 amps, which equals 5 amps plus 12.5 amps, which equals 17.5 amps. Therefore, the branch circuit conductors must have an ampacity of at least 17.5 amps. You would then select a conductor size that has an ampacity equal to or greater than 17.5 amps, taking into account any applicable adjustment or correction factors. Similarly, to determine the minimum required rating of the overcurrent device, you would use the same calculation. The overcurrent device must be rated at not less than 125% of the continuous load. In this case, 125% of the continuous load is 12.5 amps. Therefore, the overcurrent device must be rated at least 12.5 amps. You would then select a standard overcurrent device size that is equal to or greater than 12.5 amps, such as a 15 amp breaker. It's important to remember that these are just examples, and the specific requirements for each installation may vary depending on the specific conditions. Always consult the NEC and local codes for specific requirements. When dealing with electrical installations near or around bodies of water, such as in Massachusetts, special considerations must be taken into account to ensure safety and prevent electrical hazards. The NEC provides specific guidelines and requirements for these types of installations, addressing issues such as grounding, bonding, and the use of ground fault circuit interrupters, or GFCIs. Grounding is a critical aspect of electrical safety, especially in wet or damp environments. The purpose of grounding is to provide a low impedance path for fault current to return to the source, allowing the overcurrent protection device, such as a circuit breaker or fuse, to trip and energize the circuit. In areas near water, the risk of ground faults is high due to the increased conductivity of water. The NEC requires that all metal enclosures, raceways, and equipment be properly grounded to minimize the risk of electric shock. This is typically achieved by connecting these metal parts to a grounding electrode system, which consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. Bonding is another important safety measure that involves connecting all metal parts of an electrical system together to create an electrically continuous path. This helps to equalize the voltage potential between different metal parts, reducing the risk of electric shock. In areas near water, the NEC requires that all metal parts that are likely to become energized be bonded together, including metal fences, railings, and boat docks. GFCIs are devices that are designed to protect people from electric shock by monitoring the current flowing through a circuit. If a ground fault occurs, the GFCI will quickly trip and de-energize the circuit, preventing electric shock. The NEC requires the use of GFCIs in many locations near water, such as bathrooms, kitchens, and outdoor receptacles. Specifically, all 125-volt, 15 and 20 amp receptacles located within 6 feet of a sink or water source must be GFCI protected. Additionally, all receptacles located outdoors, in boathouses, or on boat docks must be GFCI protected. In addition to these general requirements, the NEC also provides specific guidelines for electrical installations on boat docks and in marinas. These guidelines address issues such as the location of receptacles, the use of weatherproof enclosures, and the installation of overcurrent protection devices. For example, the NEC requires that all receptacles on boat docks be located at least 12 inches above the deck surface and be protected by a weatherproof enclosure. Additionally, the NEC requires that each boat slip be provided with its own individually metered electrical service, with overcurrent protection located at the point of supply. When planning and installing electrical systems near water, it is essential to consult the NEC and local codes to ensure that all applicable requirements are met. It is also recommended to hire a qualified electrician who is experienced in these types of installations. By following these guidelines and taking the necessary precautions, you can help to ensure the safety of people and property in areas near water. In Massachusetts, where there are numerous coastal areas, lakes, and rivers, these considerations are particularly important. Remember that electricity and water can be a dangerous combination, and it is always better to err on the side of caution when it comes to electrical safety. Now let's explore some of the specific NEC articles that are relevant to electrical installations near water. NEC Article 547 covers agricultural buildings, which often have wet or damp locations due to animal waste and cleaning processes. This article requires the use of specific wiring methods, such as type UF cable or PVC conduit, to protect conductors from moisture and corrosion. It also requires the use of equipotential planes in areas where livestock are housed to minimize the risk of stray voltage. NEC Article 680 covers swimming pools, fountains, and similar installations. This article provides detailed requirements for grounding, bonding, and GFCI protection to prevent electric shock hazards. It also specifies the minimum distances that electrical equipment must be located from the water's edge. NEC Article 555 covers marinas and boatyards. This article provides requirements for wiring methods, grounding, bonding, and GFCI protection in these environments. It also specifies the requirements for shore power receptacles and the installation of ground fault protection for personnel, or GFP, devices. GFP devices are similar to GFCIs, but they are designed to protect equipment rather than people. They trip at a higher current level than GFCIs, typically 30 mA, and are used to prevent damage to electrical equipment due to ground faults. In addition to these specific articles, there are also several general NEC articles that are relevant to electrical installations near water. These include NEC Article 250, which covers grounding and bonding, NEC Article 300, which covers wiring methods, and NEC Article 406, which covers receptacles. When working on electrical installations near water, it is important to carefully review all of these applicable NEC articles to ensure that the installation is safe and compliant. Remember that the NEC is a minimum standard, and local codes may have additional requirements. Always check with the local electrical inspector to determine the specific requirements for your area. Furthermore, consider the corrosive effects of saltwater environments, particularly in coastal Massachusetts. Saltwater can accelerate the corrosion of metal components, leading to premature failure and increased risk of electrical hazards. To mitigate these effects, it is important to use corrosion-resistant materials, such as stainless steel or copper, and to apply protective coatings to exposed metal surfaces. Additionally, regular inspections and maintenance are essential to identify and address any signs of corrosion before they become a problem. In summary, electrical installations near water require special attention to detail to ensure safety and prevent electrical hazards. By following the NEC guidelines, using appropriate materials, and performing regular maintenance, you can help to create a safe and reliable electrical system in these challenging environments. Remember to always consult with a qualified electrician and local authorities to ensure compliance with all applicable codes and regulations.